In this example, let's consider a square body whose dimensions are d by d, and d is given as 100 millimeters. And let's assume that the body is in a state of stress, which is given as shown here. So we have a normal stress that's varying in the x direction, and we have a no normal stress in the y direction, so varying in the x direction linearly. And there's a shear stress that varies in the y direction. So this is my setup here, and beta is a parameter, and it's given as 10 MPa, so 10 megapascals. And let's first check whether this state of stress renders the body to be in equilibrium, and then also ask the question of what the resultant force and moment on the right side here is. So across this entire face here, I'd like to know what the total force is and the total moment on that side there. So to check equilibrium, we'll check our equilibrium equation. So we don't have to worry about the shear or the moment equilibrium about the z-axis, because we can see immediately that the stress is symmetric here, so sigma xy equals sigma yx. But we do have to check force equilibrium in the x and the y direction. So force equilibrium in the x direction is given by the derivative of sigma xx with respect to x plus the derivative of sigma yx with respect to y plus the body force. No body forces in this problem. And so we see that that indeed is equal to 0. Sum of the forces in the y direction is given to us by the derivative of sigma xy with respect to x plus the derivative of sigma yy with respect to y plus the body force in the y direction. No body force in this problem. And this is also seen to be equal identically to 0. So at every point in the body we have force equilibrium in the x, force equilibrium in the y, and moment equilibrium about the z. So the z, again, moment equilibrium comes to us because sigma xy equals sigma yx. So that checks out there. Okay. Now the second part of the question is, what is the resultant force and moment across the right side face there? So to get the resultant force, we need to add up the stresses across that face. And so if I integrate the traction vector over that face and multiply, say, by the thickness of the body, so it's a 2D problem, so we have to know what the thickness is, then the traction vector is beta, and the x component, and the y component is minus beta y over d, and then we integrate that with respect to y. And we'll go ahead and assume that the thickness is equal to 1 millimeter to kind of make things drop out, but we can do this quadrature here. It's rather simple. The x component is constant and the y component is linear. So if we integrate that, we have this result, and if I plug in the parameters, I find that the total force is 1,000 newtons in the x direction and minus 500 newtons in the y direction. So we have a force vector here that looks something as follows. Now, for the moment itself, we have to calculate the moment, and let's go ahead and calculate the moment relative to the origin of the coordinate system. So we'll have the lever arm here is going to be x, just the position vector, to a point along the side. So to any arbitrary location here, we'd have this vector x, components x and y, but the x component is equal to d, so that's dy. And then there's a force per unit area acting over here, which is our traction vector, t, so that's the sigma transpose n as a vector. And we have the thickness t, so there's two t's here. It's a little unfortunate in the notation I picked, but thickness, position vector, cross product, force per unit area is now going to be beta in the x component and minus beta y over d in the y component. So I can take that cross product. I'll have this integrand here pointing in the z direction. I can compute the integral. It's minus t beta d squared in the z direction. If I plug in the parameters I have, then I find out that I have 100 kilonewton millimeters moment about the z-axis. It's a 2D problem, so there's only one component to the moment anyways.